Life on Earth is said to be carbon-based. Broadly speaking, this means that carbon acts as a scaffolding agent for biomolecules. Biomolecules themselves are large organic molecules which are involved in life's processes. Now, organic molecules are carbon-based molecules with hydrogen atoms bound to the carbon atoms. For example, carbon dioxide and carbon tetrachloride are not considered organic molecules. Carbonic acid has two hydrogen atoms on it, but since they aren't bound to the carbon, it isn't considered an organic molecule. Although it should be mentioned that oxalic acid and urea are often considered organic molecules, even though they don't have carbon atoms bound to hydrogen atoms. Because of the way various functional groups can be put together and molecules can be joined together, organic molecules are incredibly diverse, and it's for this reason that they can be assembled into biomolecules. In today's video, we'll see how abundant these molecules are in the cosmos. We'll start by looking at the cold expanse of interstellar space. Now, we often think of space as a vacuum. However, it isn't completely empty, with an average density of 100,000 atoms per cubic meter. For comparison, in Earth's atmosphere at sea level, there's roughly 5.4 times 10 to the 22nd atoms per cubic meter. The most abundant element in the universe is hydrogen at 73% and helium at 24%. The third most abundant element is oxygen at 1.04%, followed by carbon at 0.46%. Helium doesn't form any compounds, which means that most molecules in the interstellar medium will be composed of hydrogen, oxygen, and carbon, which constitutes the majority of our biomass as well. Because hydrogen is so relatively abundant, space can be said to be a highly reducing environment compared to Earth, i.e., ideal for the formation of organic molecules. While most of the gases in our atmosphere are in the form of molecules, in the interstellar medium, this isn't the case. Roughly 80% of the hydrogen out there is in the form of atomic hydrogen, while 20% is in the more familiar diatomic hydrogen molecule. This also holds true for most of the oxygen and carbon atoms. Apart from stray atoms and molecules, there are also microscopic bits of dust composed of various ices in the interstellar media. Free-floating atoms will bind to these dust particles, and should a carbon atom do this, it will spontaneously react with other free-floating atoms. A carbon atom on its own has 4 unpaired electrons in its outer orbitals. Because other free-floating atoms have unpaired electrons, they will fill each other's orbitals to form molecules. This results in the formation of single carbon molecules such as carbon monoxide, methane, methanol, and formaldehyde. When these molecules form on ice particles, they will in turn add to the mass of the particle. These particles will be primarily composed of water ices, with the core of the particle being almost entirely water ice, with organic molecules occurring mainly on the outer surface. When these dust grains travel close to stars, they will then be sublimated due to the radiative heating, releasing these single carbon organic molecules into the interstellar medium. However, using spectroscopy, we've discovered more complex organic molecules including alkanes and cyanamide in the interstellar media. Now, the temperature of the interstellar medium is usually less than 10 degrees Kelvin, far too low for any synthesis reactions usually employed on Earth to assemble multi-carbon molecules from single carbon ones. So how did these come about? In space, high-energy cosmic rays fly through the medium, and when they strike a molecule, they can be energetic enough to knock off an electron, forming a free radical. This can react with another radicalized organic molecule to form a larger one, allowing synthesis reactions to occur even in the freezing depths of interstellar space. Two molecules that seem particularly common based on absorbance bands between 5 and 7 micrometers are formic acid and ethanol. These would have resulted from the formation of formaldehyde in water and methane and methanol radicals respectively. Because the interstellar medium is so cold, organic molecules which exist as reactive intermediates here on Earth can persist for many years. One variety of these highly reactive molecules which have been detected are polyenes, which exist as chains of carbon atoms linked by alternating single and triple bonds. It's important to note that the interstellar medium isn't homogeneous. There are clouds or nebulae which can span many light years across. These nebulae typically have densities 1,000 times greater than the rest of the interstellar medium. This makes them comparable to the Moon's atmosphere, which may seem like a vacuum to us. However, over the vastness of interstellar space, this seemingly thin material can form majestic shapes. These are also prime spots for cosmochemistry. The rate of molecule formation will be approximately the product of the concentration of the atoms which compose it multiplied by some constant k. So, if the abundance of the atoms in the nebulae is 1,000 times greater than the rest of the interstellar medium, the rate of molecule formation will be 1,000,000 times greater. This means that a much greater fraction of the matter in the nebulae will be in the form of molecules versus existing as lone atoms. Apart from methanol and ethanol, vinyl alcohol is quite common in nebulae. Some other organic molecules detected in high abundance include acetonitrile, acetaldehyde, cyanocetylene, and formamide. Furthermore, benzene has been detected and is known to form polyaromatic hydrocarbons, or PAHs. So, complex organic molecules, or COMs, exist in the denser regions of interstellar space. Now, if you look at many of the organic molecules identified in the interstellar medium thus far, one thing that stands out is most have carbon-carbon double bonds. This seemingly contrasts with the notion that since there is such a high hydrogen to carbon ratio in the universe, the interstellar medium is a very reducing environment, and thus one would expect organic molecules to be saturated with hydrogen. This largely comes down to a sampling bias. Molecules with double bonds are easier to detect via spectroscopy, and thus will be more readily identified, but saturated hydrocarbons like alkanes are certainly more abundant. Organic molecules with a cyanide, also known as a nitrile group, are easiest to detect because they have the largest dipole moment. The detection of nitrilated versions of organic molecules, such as cyanoethylene, in a molecular cloud is a good indication that the base molecule, along with other derivatives with various functional groups, i.e. amino, methyl, and hydroxyl groups, are present as well. When we look at the interstellar medium, we observe less nitrogen, mostly in the form of ammonia, than we would expect based on its overall abundance in the universe. Recent research has indicated that the missing nitrogen is incorporated into the scaffold of polyaromatic hydrocarbons. When some of the gas condenses, the slowly increasing gravity will draw in more gas, increasing the pressure in the core region until nuclear fusion is initiated and a star is born. During this early protostar phase, the accumulation of gas will further accelerate cosmochemical reactions. Apart from the aforementioned organic molecules, dimethyl ether, methyl formate, and propene are relatively abundant in the gases coalescing to form protostars. One molecule of particular interest detected in the hottest region of what could be called the interstellar medium, i.e. the part that is about to form a star, is glycoaldehyde. This is the simplest sugar and can act as a precursor to the synthesis of larger sugars. In the lower density regions of the stellar nurseries, heating from nearby nascent stars will rapidly sublimate ice grains, releasing their constituent organic molecules into the gaseous phase. Here, the greater density and higher temperatures facilitate chemical reactions between free-floating molecules versus those bound to dust particles. It is still very cold in these regions, meaning only exothermic reactions will occur. But exothermicity often won't be enough because at such low temperatures, the molecules wouldn't have enough energy to overcome the activation energy barrier. One way this could be circumvented is via quantum tunneling, which produces transient free radicals which will spontaneously react with one another. In stellar nurseries, there are two main kinds of gaseous phase reactions: ion-neutral and neutral-neutral reactions. Because of their low activation energies, it was long thought that reactions between ionized and neutral organic molecules dominated the synthesis of complex organic molecules in stellar nurseries. However, recent research has shown that even though these reactions will proceed at a greater rate, the large quantities of energy released by them will also end up disassociating the resulting complex organic molecules. Neutral-neutral reactions are usually driven by the formation of transient free radicals. This can either be the result of the aforementioned tunneling or the molecule being struck by a lower energy photon. Once the protoplanetary disk forms around the nascent star, the outer part of the disk is characterized by a relative decrease in the abundance of oxygen-containing organic molecules such as alcohols, ketones, and ethers compared to the interstellar medium, and an increase in the concentration of nitrogen and the overall abundance of carbon. So, in this region, hydrocarbons and nitriles are more prevalent. There are a number of competing hypotheses as to why this is, but the most likely explanation is that since oxygen-containing organic molecules are more polar, they have a higher sublimation temperature. So, oxygen-poor organic molecules will be more readily sublimated into the gaseous phase when heated by the light of the protostar. The more oxygen-rich organic molecules remaining as ices will be more readily incorporated into early planetary bodies as the dust grains coalesce into them. Closer to the protostar, the temperatures are much higher, which allows UV light to facilitate photochemical reactions versus the more energetic but less abundant X-rays, which produces complex organic molecules in the planet-forming region. These can be longer-chain hydrocarbons or the monomeric forms of biomolecules such as fatty acids, amino acids, and pyrimidines. As stars approach the end of their life, there is some interesting organic chemistry going on as well. When stars like our Sun use up the hydrogen in their core, they will begin to fuse helium into carbon and oxygen. As they do this, they will swell up to form a red giant. Although most of the carbon produced will remain in the core, some of it will end up in the rest of the star and be ejected as part of the solar wind. Since the surface of red giants are quite cool, aromatic and aliphatic hydrocarbons can form in their circumstellar region. This area is usually hot enough for the molecules to overcome the activation energy barrier, allowing the reactions to proceed thermochemically versus photochemically. Also, due to the cooler temperature of the surface of the star, a much smaller fraction of the light particles emitted will be energetic enough to initiate photochemical reactions. When the star dies, it will form a planetary nebula where the outer layers of the star are blown off into space while the remaining core becomes a white dwarf. In the planetary nebula, various complex organic molecules will coalesce into solid carbonaceous particles in the gaseous medium. In the accretion disks which exist around black holes, polyaromatic hydrocarbons have been detected, while other organic molecules which occur in interstellar space have not been identified. This is mostly because polyaromatic hydrocarbons are far more stable than other organic molecules, and thus won't be as readily sputtered by the intense radiation. Going closer to home, there is a region around the solar system known as the Oort cloud. This region exists as a giant sphere which spans from 2,000 astronomical units to 1 light year from the Sun. While influenced by the Sun's gravity, its composition more closely resembles that of interstellar space. This region hosts trillions of comets, and some of them will have an orbit which temporarily brings them into the inner solar system. Probes have been sent up to analyze cometary material, and in it, we found all the aforementioned small organic molecules identified in the interstellar medium, along with ethylene glycol. Furthermore, we found glycine, the simplest amino acid, in the tail. As solar radiation evaporates the surface of a comet to produce a tail, the solar wind particles would generate ammonia and acetic acid radicals, which will in turn react to form glycine. The other main variety of planetesimals in our solar system are bodies known as asteroids. Most of us are familiar with the two main varieties, that being stony and metallic, but it would be more useful to divide asteroids into three categories. When the solar system was being born, many planetesimals formed in the circumstellar disk, i.e. the planet-forming region. Many of these continued to coalesce to form planets. The energy from all these collisions melted the material, and the denser metallic material sank to the core, while the lighter rocky material rose to the surface. This process is known as differentiation. Some of these early planetary bodies were destroyed in collisions, spewing their contents into space. Metallic meteorites were once part of the core of these destroyed planetary bodies. A variety of stony asteroids known as chondrites are what remains of the original planetesimals that hadn't undergone differentiation. So, the three types of asteroids are metallic, chondritic, and quote-unquote stony, or those that were part of the surface layer of a planetary body that was destroyed. Chondrites are of particular interest to cosmochemists because they can tell us a lot about the primordial composition of the solar system. One variety, which composes 4.6% of all the meteorite falls, are carbonaceous chondrites. As their name suggests, They have a relatively high carbon content, including organic molecules. Polyaromatic hydrocarbons contain little under 20% of the carbon found in the interstellar medium. Isotopic analysis of polyaromatic hydrocarbons in the carbonaceous chondrite Ryugu have indicated that the naphthalene, chloranthalene, and pyrene were originally synthesized via ice-grain cosmic ray reactions in the cold interstellar medium and were collected by the gravity as parts of the nebulae coalesced to form the solar system. Meanwhile, phenanthrene and anthracene were synthesized in the high-temperature gaseous phase after the material coalesced to form the circumstellar disk. A wide variety of organic molecules have been identified in carbonaceous chondrites, such as long-chain carboxylic acids, aliphatic amines, amino acids, and recently nucleobases. The nucleobases were likely produced via photochemical reactions in the gaseous phase, while the amino acids were produced via Strecker reactions between aldehydes and ammonia, with various metal cations in the asteroids acting as catalysts. During formation, pockets of liquid water could form in the chondrite, allowing aqueous phase organic synthesis reactions to occur. Low-temperature hydrothermal reactions are characterized by the higher abundance of saturated and monounsaturated carboxylic acids, while high-temperature ones are characterized by the sulfurization of the amino groups on organic molecules. Analysis of the surface spectra of the largest asteroid Ceres, which has a surface with a composition similar to the differentiated stony meteorites, has identified regions of the surface rich in organic carbon. About 20% of its weight is in the form of aliphatic and aromatic hydrocarbons, with more aliphatic compounds than carbonaceous chondrites. Overall, the organic matter in stony meteorites would have been subjected to a greater degree of hydrothermal alteration, since it would have been heated or at least kept above 0 degrees Celsius in the parent body before being frozen in space and the water was sublimated. Carbohydrates have also been recently found in meteorites. Both amino acids and sugars have two stereoisomers, the L and D isomers for a given molecule. Life on Earth uses the D isomer of sugars and the L isomer of amino acids. Interestingly, while abiotic synthesis production produces an equal mix of the D and L isomers of sugars and amino acids, also known as a racemic mixture, in extraterrestrial material, the D isomer of sugars and the L isomer of amino acids are slightly more common than the other stereoisomers. Now, instead of looking at planetesimals, we can look at planetary bodies. We can start with the Kuiper Belt. This is a region which spans from 30 to 50 astronomical units from the Sun, and mostly includes dwarf planet icy bodies, most famously Pluto. The ice in this part of the solar system is mostly water, but a sizable fraction is composed of ammonia. Out here, it is so cold that even what we consider volatile organic molecules are frozen. When the New Horizons spacecraft flew by Pluto, it showed a very colorful surface, which seemed to be the result of organic molecules on it. How these colors were produced is still debated, but one experiment has shown that when small organic molecules on the surface such as methane and acetylene are hit by galactic cosmic rays, it will produce aromatic molecules with up to 3 rings such as phenanthrene, phenylene, and acetylene, which can account for the colors observed. Some of these carry the structural motifs of nucleobases via unsaturated linkers. In the atmosphere of gas giants, methane is a minor constituent and has even been detected in the atmosphere of an extrasolar gas giant. Methane is fairly rare in the true gas giants, i.e. Jupiter and Saturn, but more common in the ice giants, Uranus, and even more so in Neptune. Methane will give an atmosphere a blue color, which is why Uranus is turquoise and Neptune is blue. Also, methane will condense to form frozen clouds high in the atmosphere of Neptune. While not much in the way of organic chemistry is going on in the atmosphere of gas giants, on their moons it's another story. Neptune's largest and only major moon is Triton, and it has a retrograde orbit, indicating that it was once a Kuiper Belt object that was captured by Neptune's gravity. Triton is the coldest body in the solar system and has a thin atmosphere made up primarily of nitrogen, with a surface pressure of 14.3 microatmospheres, with trace amounts of methane and carbon monoxide, 0.025 and 0.06% respectively. These will react with each other along with nitrogen ionized by Neptune's magnetosphere to produce an assorted variety of nitrogen-rich organic molecules known as tholins. Some of these tholins are the nucleobases used in genetic material. These organic tholins will then precipitate out to form a faint haze layer which extends up to 50 kilometers above the surface. The interior of Triton is warmed via tidal heating thanks to its orbit around Neptune. This results in geysers made of liquid nitrogen rising many kilometers into the atmosphere. Within these plumes are small organic molecules which rapidly freeze out in the cold air. These ice particles are carried downwind and are laid close to the geyser, and irradiation by ionized particles, possibly from bits of the solar wind captured in Neptune's magnetosphere, leads to the formation of even larger tholins than those in Triton's atmosphere. These form black streaks on the surface next to the geyser, contrasting the pink snow made of frozen nitrogen. Not much in the way of organic chemistry is going on the moons of Uranus, but on the satellites of Saturn, it's a very different story. The outermost of Saturn's major moons is Iapetus, which has a number of unusual features such as an equatorial mountain range and a dark leading hemisphere contrasted with a light-colored trailing hemisphere. The light gold-covered side is composed of water ice, while the darker surface is covered in aromatic and aliphatic hydrocarbons. It's believed that the progenitors of the surface organic material were moderately sized organic molecules produced via thermochemical reactions between methane and cyanide in the interior of Iapetus. Upon reaching the surface, it was irradiated by ionizing particles from the sun, producing larger organic molecules. This organic matter would have initially been yellow, but as it was quote-unquote cooked by radiation, it would have first turned brown and then black. Water is more readily sublimated on the leading hemisphere than the organic matter, causing it to go through the thin atmosphere to the other side, resulting in the color dichotomy between the hemispheres. Dione, another major moon of Saturn, has relatively high levels of organic material on its surface, which is exposed to ionizing radiation. However, there isn't as much organic matter as there is on Iapetus, so it has a red versus black color. From the standpoint of purely organic, i.e., non-biological chemistry, Saturn's largest moon Titan is arguably the most fascinating body in the solar system. Titan is the only moon in the solar system with a thick atmosphere, which has a surface pressure of 1.6 atmospheres and is composed mostly of nitrogen. In this atmosphere, methane composes roughly 5% of all molecules, with trace amounts of other 1 and 2 carbon organic molecules. Here, it acts in a similar manner to the water on Earth, with a methane quote-unquote hydrologic cycle. Clouds of methane form in the troposphere, and from some of these, methane rain will fall to the surface. Titan's surface is composed of water and ammonia ice, and at a surface temperature of 94 degrees Kelvin, water ice has the same mechanical properties of granite. The methane rain flows over the rock-like icy surface, and some of it will pool in low areas to form hydrocarbon lakes. Some of the more prominent lakes are the Punga, Ligeia, and largest of all, the Kraken Mare. The lakes in the equatorial region are believed to contain significantly more ethane than the clouds, possibly up to 50% by mass, because lakes made of pure methane would evaporate more rapidly. However, the radar signatures of the polar lakes have indicated that they are almost pure methane, and at such latitudes, the colder temperatures would limit evaporation. Titan also has a series of dunes near its equator. It's not known if these are composed of water ice or organic molecules, but if the latter is the case, a recent experiment elucidated how they could have formed. Cosmic rays will bombard acetylene ices which condense on the surface, forming larger polyunsaturated organic compounds within the icy molecular lattice. When the acetylene melts, these larger molecules are left behind, forming grains. As this process is repeated year after year, the grains build up to form dunes of organic material. Going up in Titan's atmosphere, there is a much more gradual decrease in the temperature in the troposphere. So, a smaller fraction of the atmospheric methane precipitates out as clouds as the altitude increases when compared to water vapor on Earth. As a result, the methane concentration of the tropopause is one-third that of the surface, while the concentration of water vapor at Earth's tropopause is 1/300th that of the surface. At Titan's tropopause, UV light from the sun will strike methane molecules, initiating photochemical synthesis reactions, which initially produce short-chain hydrocarbons and other small organic molecules. These are not as volatile as methane and thus precipitate out as droplets, forming a layer of condensate haze between 60 and 80 kilometers high. This layer gives Titan its distinctive yellowish-orange color. Carbon isotope analysis has indicated that while methane is being lost to photodissociation, it is also being replenished. The most likely source is cryovolcanism, or volcanoes on the surface, which release a slushy mixture of water and ammonia. Dissolved within this quote-unquote lava are various gases, including methane, which are released into the atmosphere. Nitrogen molecules are split by high-energy cosmic ray particles, and these will then react with organic molecules in the condensate haze to form amino and nitrile groups. The photochemical synthesis reactions will continue to make larger and larger organic molecules, which will exist as solids within the haze droplets. Higher in the atmosphere, the pressure is too low for most chemicals to exist as a liquid, causing the smaller organic molecules in the droplets to evaporate and/or boil, leaving only the solid-state larger molecules. These form a thin layer of Tholen haze, which can be seen as an indigo halo around Titan. Another very interesting moon of Saturn is Enceladus. This is the second smallest and second closest of Saturn's major moons. It has an icy crust with little cratering, implying recent resurfacing. There are also geysers coming up from a subsurface ocean through gaps in the ice. The plumes extend tens of kilometers into space, allowing probes to fly through them and analyze their content. In these, we found many small organic molecules such as methane, hydrogen cyanide, acetylene, ethane, and methanol. We've also recently identified larger organic molecules such as polyaromatic hydrocarbons and humic compounds. The polyaromatic hydrocarbons were likely originally in material that accreted to form Enceladus later in its formation. There are a number of hypotheses as to how the humic compounds are formed. One scenario is that minerals under the icy crust catalyze the synthesis of these compounds from smaller organic molecules. The precursors would more likely have been methanol and formaldehyde as opposed to methane, since it's comparatively inert. Another hypothesis is stated that the humic substances are biogenic, but that's another story. Going to Jupiter, the first moon we'll look at is Europa. Like Enceladus, it has a lightly cratered icy crust, suggesting recent resurfacing. It's also believed that Europa has a subsurface ocean beneath its icy crust. On some of the surface grooves, we can see a brownish color, and this is the result of organic molecules in the crust. These were likely originally smaller organic molecules brought to the surface by water upwellings. Europa lies within Jupiter's Van Allen radiation belts, where solar wind particles are trapped by its powerful magnetic field. These would form organic radicals in the ice, which would then polymerize with each other to form larger organic molecules. The crystalline icy lattice could also act as a catalyst to produce these large organic molecules, which give the streaks their color. Aliphatic aldehydes have also been detected on the surface of the moons Ganymede and Callisto. However, the concentration of organic molecules are nowhere near those present on Europa or Iapetus. Moving into the inner solar system past the frost line, we'll first look at Mars. The red planet gets its name from iron oxides which cover its surface. Sulfate minerals are also common on the surface, and the atmosphere is made of 95% carbon dioxide. Basically, it's a very oxidizing environment. However, locked within 3+ billion-year-old mudstones from Gale Crater are some simple chlorinated organic molecules such as chlorobenzene, chloropropane, and chloroethane. Although the presence of organic molecules on Mars has been used to argue for the presence of life in the ancient past, there are other methods by which organic molecules could have been produced. But how did they become halogenated by the chlorine atom? The most likely explanation is that alcohol groups on them were pyrolyzed in the presence of calcium perchlorates. Perchlorates are a reactive ion, which make up 0.5% of the weight of the Martian topsoil. Methane is a trace constituent in the Martian atmosphere, and its abundance can vary from 60 parts per billion to below the 0.5 parts per billion detection limit. There is a high degree of both spatial and temporal variation in atmospheric methane concentrations. Methane levels peak in late summer, early autumn of the northern hemisphere, and reach their minimum in the late winter, early spring. The methane appears to be released from the Amazonias planitia and the Utopia basin. The source of this methane is a hotly debated topic. One hypothesis is that the Martian mantle is more reducing than that of Earth's, so more of the carbon contained within it will be in the form of methane versus carbon dioxide, and the methane we're observing is being released by far underground magma. A second explanation is that subterranean serpentinization reactions produce hydrogen, and this then reacts with carbon dioxide, using various minerals as catalysts to produce methane. A third hypothesis is that it's being produced by microbes, but, as is the case with Enceladus, that's a topic for another video. On our moon, we found amino acids from lunar regolith brought back to Earth. We've also detected larger quantities of organic molecules in the ices lying within the fully shaded parts of the polar craters of the Moon and Mercury. These were probably delivered by asteroid and comet impacts. Now finally, we come to Earth. The organic geochemistry of the Earth could be a video in and of itself. So, here, we'll look at the prebiotic chemistry of our planet. It had long been thought that the early Earth had a highly reducing atmosphere, rich in methane, ammonia, and hydrogen sulfide. This was the basis for the famous Miller-Urey experiment. Here, sparks of electricity, simulating lightning, were passed through a mixture of such gases, which led to the production of amino acids. The results of this experiment seemingly reinforced the primordial soup hypothesis, or the idea that the first organisms emerged from a vast pool of organic molecules. However, analysis of zircons from 4 billion years ago have indicated that the primordial atmosphere was not reducing but inert, being mostly composed of molecular nitrogen, carbon dioxide, and argon. The reason for this lies deep down in the core mantle boundary. Here, the three redox states of iron, that being metallic, ferrous, and ferric iron, exist in equilibrium concentrations. Of these, metallic iron is the most dense, while ferric iron is the least dense. Because Earth is large for a terrestrial planet, it has a greater acceleration due to gravity, causing more of the metallic iron to go into the core and more of the ferric iron to go into the mantle. Here, the ratios of ferric to ferrous iron are out of whack, and it has to get electrons to restore the equilibrium. It gets these from ammonia, hydrogen, methane, and sulfides, producing nitrogen, water, carbon dioxide, and sulfur dioxide. These gases were then released by volcanoes to form the primordial atmosphere. While passing lightning through a mixture of these gases will produce a small quantity of organic molecules, it won't give you a primordial soup. Now, during the Hadean Eon, asteroids and comets regularly fell to the surface of the Earth. These are rich in organic molecules, so you might think that they could deliver their organic content, and we thus get a primordial soup that way. This wouldn't work either. While there is virtually no oxygen in the atmosphere, interactions between water and chloride ions would produce highly reactive perchlorates on the surface, which would rapidly oxidize organic carbon. So, if there was to be any accumulation of organic molecules on the early Earth, it would have to be from a localized source of production. While most organic matter on the Earth is produced via photosynthesis, there are geochemical processes that produce organic molecules from inorganic carbon and hydrogen. These usually happen in hydrothermal systems. The variety we're most familiar with are volcanic vents, also known as black smokers. Hydrogen and carbon dioxide, dissolved in the magma, flows up into the vent column, and in the superheated water, iron-sulfur minerals like rigite and mechanowite will catalyze the production of simple organic molecules. These reactions are known as Fischer-Tropsch type synthesis reactions. It involves an inorganic carbon oxide binding to a metal and then being incrementally reduced by the addition of molecular hydrogen. This process was first described using carbon monoxide. Once the carbon-metal complex is formed, a hydrogen will react with it, either releasing the carbon as a formaldehyde or adding an alcohol group to it. Then another hydrogen could react with it, releasing the hydroxyl group as water and forming a methyl group, which can then be released as methane. However, if there is another carbon adjacent to it, they can bind to each other, releasing the hydroxyl group as water. Another hydrogen will further reduce the second carbon, causing it to become detached from the metal atom. This process will repeat itself, further elongating the hydrocarbon chain. At the point each additional carbon is added, there will be a probability that it will be released. So, a slew of alkane chains with different lengths will be generated, with the concentration decreasing as the number of carbon atoms increases. Cobalt impurities more readily facilitate the transfer of the methyl group to a nascent chain, so their presence will lead to longer chains. Apart from carbon monoxide, Fischer-Tropsch type synthesis reactions which use carbon dioxide have recently been described. The binding of carbon dioxide to metal catalysts is enhanced by the presence of potassium oxides, and the formation of two carbon molecules is promoted by the presence of aluminium oxides, although the mechanism by which this happens is yet to be described. While the reduction sequence of carbon monoxide is formaldehyde, methanol, and methane, that of carbon dioxide is likely formic acid, formaldehyde, methanol, and methane. Carbon monoxide-based Fischer-Tropsch synthesis reactions occur at temperatures between 150 and 300 degrees Celsius, while those which use carbon dioxide as a substrate happen between 300 and 400 degrees. The high temperatures inside black smokers allow these reactions to occur. While some black smokers host temperatures hot enough to allow for the reduction of carbon dioxide, another possibility is that the gas shift reaction produces carbon monoxide from carbon dioxide and hydrogen. So far, we've only seen methane being produced in volcanic vents, but there are other types of hydrothermal systems. The other variety are serpentinizing vents, or white smokers. Instead of being heated by interactions between magma and water, these are heated by water chemically reacting with ultramafic rocks like olivine and pyroxene. This process produces serpentine, magnetite, and hydrogen. The hydrogen will react with inorganic carbon to produce organic molecules. Compared with black smokers, serpentinizing vents are sulfur poor and don't have that many iron sulfur minerals to act as catalysts. One possibility is that magnetite can act as a substitute. These systems produce a much wider variety of simple organic molecules. On the prebiotic Earth, both volcanic and serpentinizing systems would have been more abundant than they are now. Furthermore, a larger fraction would be composed of serpentinizing systems. This is because the crust hadn't yet chemically differentiated from the mantle, i.e., get more of the lighter felsic rocks versus the heavier mafic rocks. So, ultramafic rocks would be far more abundant on the surface. The mantle of the early Earth would have been much hotter, meaning more volcanic vents would have been hot enough to produce organic molecules from carbon dioxide. Not only was carbon dioxide far more abundant than it is today, without an ozone layer, high-energy UV photons would penetrate deep into the atmosphere, where they would react with carbon dioxide and water to produce hydrogen, oxygen, and carbon monoxide. This carbon monoxide could then be fed into abiotic Fischer-Tropsch type synthesis reactions, enhancing the total production of organic molecules on the prebiotic Earth. So, while it's doubtful there were oceans full of organic carbon on the early Earth, there were likely many localized sources of production. Also, many geochemists used various redox proxies to identify whiffs of oxygen in the ancient atmosphere, to argue that oxygenic photosynthesis evolved very early on, but there are abiotic mechanisms by which oxygen could be produced, such as the one described. But when did such processes begin? When the Earth first formed, it was a molten mass and was then struck by the Mars-sized body Theia. The debris from this collision formed our moon. So, when did the surface cool sufficiently for liquid water to exist? Well, in geologic times, the boundary between the Archean and Hadean eons is defined by the age of the oldest rock in existence, the Acosta gneiss, which has been dated to 4 billion years ago. However, there are crystals known as zircons, some of which were formed before 4 billion years ago, and then incorporated into rocks which formed afterward. One of these detrital zircons, found in the Jack Hills region of Australia, has been dated to 4.3 billion years ago, and analysis of its oxygen isotope composition indicated that it formed in liquid water. So, we know that by the mid-Hadean, the surface had cooled sufficiently for liquid water to exist, and aqueous phase organic synthesis reactions could occur. Now that we have the means to produce simple organic molecules, is there a way we could assemble them into biomolecules? Well, if an alkane chain is linked to a carbonate ion bound to a mineral, it will form a carboxylic, i.e., fatty acid. So, we already have lipids, one of the four classes of biomolecules, from entirely inorganic starting materials. Also, when formic acid in an assortment of short alkanes dries on montmorillonite clay, it will also result in the production of lipids. Now, what about carbohydrates? Well, boiling a solution with formaldehyde in it will result in the formation of simple sugars. How about nucleic acids? These are composed of a sugar, ribose, a phosphate group, and a nitrogenous base. Boiling a solution of cyanide, cyanocetylene, and urea will result in the production of purines like adenine. Whenever we talk about polymerization in a biochemical context, we usually think of assembling larger molecules out of monomeric versions of biomolecules, cellulose from individual glucose molecules, or proteins from individual amino acids. But we can instead see monomers as polymers of single carbon compounds. However, the assortment produced will be largely randomly put together and include many sugars and nucleobases not used by organisms. Instead, we've identified reaction sequences that produce biologically relevant sugars like ribose directly. One of these is the aldehyrization of formaldehyde and 2-glycoaldehyde phosphates, which produces a 2,4-ribose diphosphate. It's a starting point, but it would be hard to use this ribose in the construction of genetic material, since the ribose we use has a phosphate on the fifth carbon. One way this derivative could be produced is by a prebiotic reaction network which closely resembles the pentose phosphate pathway, a process our cells use to produce ribose. When some of the simpler organic molecules, like phosphenylpyruvate, used to produce ribose from, are put into an environment which chemically resembles the primordial oceans, they form reaction networks which closely resemble glycolysis in the pentose phosphate pathway. The end product of the pentose phosphate-like pathway is ribose 5-phosphate, and that of the glycolysis-like pathway is glucose 6-phosphate. These reactions appear to be catalyzed by ferrous iron ions, and at neutral and acidic pHs, the glycolysis analog dominates, and under alkaline conditions, the pentose phosphate pathway is more prevalent. So, we now can produce ribose, but there's still a problem. Both glycoaldehyde phosphate and phosphenylpyruvate are phosphorylated compounds. The phosphate ester bond, which binds the phosphate group to the molecule, is a very high energy bond. So, in order to be formed, in accordance with the law of conservation of energy, a higher energy bond has to be broken. Our cells phosphorylate organic molecules by cleaving the phosphoanhydride bond between the second and third phosphorus on an ATP molecule. The phosphoanhydride bond between the phosphorus atoms on the ATP are an even higher energy bond than a phosphate ester, and an input of metabolic energy along with complex cellular machinery is needed to replenish the phosphoanhydride in the ATP. Under most conditions, a lonely orthophosphate won't react with an organic molecule. There is a mineral known as schreibersite, an iron nickel phosphide, which corrodes in water to release high energy phosphorus species. This compound is rare in Earth's crust, but is more abundant in meteorites, which would have fallen to the surface regularly 4 billion years ago. One of the compounds released by this corrosion is pyrophosphate, which is essentially two orthophosphates held together by a phosphoanhydride bond. This can be cleaved to phosphorylate an organic molecule by its hydroxyl group, releasing the other phosphorus atom as an orthophosphate. The phosphorylation of organic molecules by pyrophosphate will be catalyzed by magnesium ions, which are abundant in serpentinizing systems. So, on the early Earth, simple organic molecules could be readily phosphorylated and fed into synthesis reaction networks to produce prebiomolecules. So, now we have ribose. Can we make nucleotides? Although it's trivial to produce nucleobases abiotically, what can be done is making the glycosidic bond between the first carbon on the ribose and the nucleobase. Instead, what likely happened was the base was built on the ribose via the addition of small nitrogenous organic compounds. More specifically, cyanamide will react with ribose to form an amino oxazole. This will then precipitate out in a crystalline form, which can purify the ribose. Later, other nitrogenous organic molecules like cyanide can be added to form the remainder of the nitrogenous base. Another mechanism involves reacting ribose with urea and phosphate using borate as a catalyst. This adds a phosphate to the fifth carbon of the ribose and the urea to the first. Again, other simple nitrogenous compounds can be added to the urea to form the nucleobase. So now we have a nucleotide, and one possibility is that borate would add a Schreiber-derived pyrophosphate to the fifth carbon, producing what's known as an activated nucleotide. Another pathway that's ubiquitous throughout all branches of the tree of life that we found abiotic analogs of is the TCA cycle. Here, acetyl-CoA is reacted with oxaloacetate to form citrate, which is then isomerized to form isocitrate. The isocitrate is then oxidized by NAD, releasing a carboxyl group as carbon dioxide to form alpha-ketoglutarate. This is then oxidized by another NAD to form succinate, again releasing the carboxyl group as carbon dioxide. Next, the succinate is oxidized by FAD, another electron carrier, producing a fumarate with a double bond between the second and third carbons. This is hydroxylated by a water to form an alcohol group, producing malate. The hydroxyl group is then oxidized, resulting in an oxaloacetate for the next turn of the cycle. While our cells use enzymes to catalyze these steps, they can be catalyzed by iron-sulfur minerals in a hydrothermal setting. On the early Earth, perchlorates or peroxides produced by reactions between UV light, metallic minerals, and water could act as oxidants to drive the cycle. In our cells, pyruvate is oxidized by NAD, bumping off the carboxyl group as a carbon dioxide, and reacted with coenzyme A to form acetyl-CoA. In the abiotic TCA cycle analogs, pyruvate will be reacted with an oxaloacetate while being oxidized directly, producing citrate. Now, nominally, it would act as a sink for organic carbon, since it's oxidizing some of it to carbon dioxide. However, two of the intermediates, oxaloacetate and alpha-ketoglutarate, are what are known as alpha-ketoacids. These can then be reacted with ammonia to produce the amino acids aspartate and glutamate, respectively. This is done via a Strecker reaction, where the ammonia replaces the ketone on the carbon adjacent to the carboxyl group, the alpha carbon, hence the name alpha-ketoacids, becoming an amino group. Serpentinizing systems from the oldest mudstones dated to 3.8 billion years ago are replete with ammonia, but how it was produced is a bit of a mystery. In a manner similar to the Fischer-Tropsch process, the Haber-Bosch process uses metal to catalyze the reduction of diatomic nitrogen to ammonia using hydrogen as the electron donor. However, since the triple bond is harder to break than the double bonds in carbon dioxide, the Haber-Bosch process has to take place under higher temperatures and pressures than the Fischer-Tropsch reactions, pressures and temperatures that wouldn't occur in naturally occurring hydrothermal systems. My hypothesis is that since the young sun would often have flares where it released many high-energy charged particles, some of these would penetrate deep into the atmosphere and generate nitrogen radicals, which would then be more reactive and could be fed into Haber-Bosch type reactions to produce ammonia. One version of the TCA cycle has the glyoxylate shunt, where the decarboxylation steps are omitted. Here, isocitrate splits into succinate and glyoxylate. The succinate is then oxidized and hydroxylated to form oxaloacetate, while the glyoxylate is reacted with another acetyl-CoA to form malate, which is then oxidized to form oxaloacetate. Since two oxaloacetates are produced, one can be the product of the cycle, while another can be reacted with another acetyl-CoA for the next turn of the cycle. This has also been observed in abiotic settings, but here a second pyruvate is added to the glyoxylate. Glyoxylate and pyruvate are the corresponding alpha-ketoacids of glycine and alanine respectively. As such, some of the intermediates could become aminated, becoming amino acids versus continuing in the cycle. In organic chemistry, there are usually minor and major products of a reaction, and in the abiotic TCA cycle analogs, there would also be minor products that couldn't be fed into the next stage of the cycle, acting as a sort of bleed-off. The presence of zinc and chromium ions will decrease the production of these minor products in the abiotic TCA cycle, i.e., increase its overall efficiency. Furthermore, copper, nickel, cobalt, and vanadium ions catalyze the Strecker reactions, which convert alpha-keto into amino acids. Apart from the aforementioned versions of the TCA cycle, there have been other attempts to derive abiotic analogs of other permutations of it. It's been shown that zinc and chromium ions, along with metallic iron, can catalyze 6 of the 11 steps of the reverse TCA cycle in acidic conditions, but can't complete a whole turn. It's also been shown that cyanide can mediate the dimerization of glyoxylate to form tartrate, which can more readily be fed into abiotic analogs of the TCA cycle on the prebiotic Earth. There has also been some work in getting TCA cycle analogs to run without metals. One experiment showed it will proceed in a cyanosulfidic environment, and another demonstrated a series of reactions involving similar intermediates to those of the TCA cycle. Both were fed glyoxylate as the carbon source, and the first ran oxidatively, while the second ran in reverse, although it couldn't fix carbon dioxide to the intermediates. Now we know that biomonomers could be produced on the prebiotic Earth, but could they be assembled into polymers? Well, for one, if a solution of amino acids with boric acid in it dries on sediment, it will result in the production of polypeptides. Also, if activated nucleotides dry on montmorillonite clay, they will polymerize into RNA oligomers. Although, those in our cells have the nucleotides linked by the 3rd and 5th carbon on the ribose, those produced via drying on montmorillonite clay will also have 5-2 linkages. Lipids won't regularly polymerize per se, but they can form other structures. At higher pHs, most of the carboxyl groups of the fatty acids will be deprotonated, i.e., have a negative charge on the oxygen. This results in the head group becoming even more hydrophilic, and lipid vesicles, hollow balls surrounded by a bilayer membrane, forming. Although these will only form at pHs greater than 8.5, should the pH decrease, the vesicles won't dissolve until it reaches 5. The presence of minerals like pyrite, quartz, hydrocalcite, and the aforementioned montmorillonite can increase bilayer membrane formation some 1,000-fold. Also, when lipid vesicles dry out, they can catalyze the polymerization of biomonomers within them. Such structures could ultimately become the membranes of the first cells. So, in summary, the building blocks of life are everywhere around us. In that sense, getting them to organize into a living thing is a matter of getting all the conditions just right. The biochemical reactions that power our metabolisms are just one of many that drive carbon chemistry throughout the cosmos. As always, if you enjoy what you see, please like and subscribe. Thanks.